Hi juniors, this video is to help you understand or give you kind of an overview of the CK12 lesson, Introduction to Exponential Models. So here's our class plan that you can see on the screen. And please know that you can do this video first, or you can look at the CK12 lesson first, or maybe you just look at the notes from this lesson that you would normally see on the Promethean board. Either one of those three in any order is just fine. So here are some jokes for the day. Ha! Happy Monday! Here are the learning targets that I would like you to have by the end of the week or by the end of next week, depending on which lesson you're choosing. The first one is I just want you to be able to model growth using an equation from a table or from a graph or from a scenario. And I also want you to be able to model exponential decay. Now, here is an example of exponential growth. This is from that CK12 lesson, again. So you can see the number of days increasing and the number of bacteria is also increasing. There's a question that asks, after day 20, how many bacteria will there be? And it will be more than 1 million. This is how fast exponential growth can occur. Then there's these things that are called progress. So you just little check-ins to see how you're doing along in the lesson. So there are 4 questions that we're going to answer. But there's a question that you need to answer first. What is a multiplier? And all that is a number that allows you to find the next number by multiplying to the current number. So let's look at an example of that. So here, true or false? This number of bacteria can be represented by a linear function. So let's look at the pattern. As the days are increasing by 1, what's happening to the number of bacteria? Well, you can see here there's 10 bacteria, but over here there's 15. Hey, something is not linear there. So this one is false. The rate of change is not constant, so it is not a linear function. But if you look over here, this one asks you for that multiplier. And what you're doing is you're taking half of one day and adding it to that day. So what's half of 20? 10. What's 20 plus 10? 30. Now let's do it again. What's half of 30? 15. 15 plus 30? You get 45. So the multiplier, 20 times 1.5, 30 times 1.5, 45 times 1.5. Right up here, we'd be getting into some decimals in that third day, but that's okay. But the multiplier is 1.5. You can always find it by going backwards. Say you took 30. Please excuse my rough writing with my computer. 30 divided by 20, and you'd get the same result as if you did 45 divided by 30, and you'd get 1.5. The next example asks you for how much bacteria after 5 days of growth. Well, if we continued that pattern, we would just multiply 1.5 by itself 5 times for the 5 days of growth, and then multiply it by that initial value. That initial value, you can think about it as day 0, not day 1, day 0. So with that multiplication, we get about 152 bacteria. The last question in this little example asks, after how many days, now we're looking for days, will the number of bacteria go past 10,000? Now, you can see the answer right here is about 16. But how could we answer it with the graphing calculator? If you look ahead in these notes, you'll see some screenshots of the calculator from the Minneapolis website. And it will take about 16 days, and you can see that from the table right here. But I'd like to show you on the calculator how to do that. So I'm going to go back up here. What I'm going to do is just start by typing in this data. I'm going to highlight it for you. 0, 1, 2, and then 20, 30, 45. So let's go to a tab for that calculator. So here's that calculator, and you just have to click start a couple times, and then the icon is up here. So to get to the data, I'm going to enter the data in the statistics plot. And if I'm going too fast for you, just hit pause and do the actions and then start play again. So the days were just 0, 1, and 2. And then the number of bacteria, whoops, we started with 20, and we went to 30, and lastly, 45. Okay, so the data is in the calculator. Now I'm going to hit Stat, and I'm going to go to Calculate. I'm going to have the calculator calculate what is the exponential model. And what you're going to have to do is go down to number 10. And that, if you see, is EXPREG, exponential regression is what that stands for. And if you hit enter, it asks you which lists. Now, if you had different lists, say list 3 or 4, you'll need to adjust that. But I'm pretty sure you'll still have it. You'll probably have it in list 1 or list 2 for your X and your Y values. And just keep hitting enter all the way down. And there it is. So this just confirms that our multiplier is 1.5. We started with 20, and it even gives you the model of an exponential equation. So once you type that in to your y equals, a is 20, b is 1.5, and we'll raise that to the x power. So 20 times 1.5 raised to the x power. Here's your variable key. And then if we hit second graph, we can clearly see, and I'm going to increase this. Remember, you can increase this by putting the cursor outside of the calculator and then Control plus or Command plus on a Mac. And I can scroll down. Notice that on the 10th day, I have over 1,000 bacteria. And then things start to grow really fast. By day 14, I'm almost at 6,000. And then at 15, there's about 800. And there you are. At 16 days, we have gone past the 10,000 mark. So here is exponential model. I'd encourage you to put this in your notebook. This is the equation that we will use to model all exponential equations. As we talk about growth or decay, this b value right here will be adjusted. But in every exponential model, there's always a starting place, an initial value, and a multiplier. Here's what it looks like from CK12. And here is the growth equation. Notice that b is what is in this parentheses. And if we're growing, then we're going to add 100% of what we currently have by some rate of change. And this rate is always a decimal. Here's an example down here of some ant population growing. 1 plus 0.5. 1.5 is your multiplier, but we are growing by 50% each day, just like the bacteria example. Let's talk about decay for a moment. When you look at this equation, notice that there's a subtraction, but the multiplier, the b, is still in these parentheses raised to the x power. So an example of decay would be definitely car depreciation. So when you drive the car off a brand new car off the lot, it is said to decrease by, say, 17%. I've even heard 14%, but the value goes down pretty quickly. So this one is decreasing by 0.87. So really the multiplier is 0.83, because we just subtract that. So that's generally what you would see in the equation. So if that multiplier is between 0 and 1, then you know you are decaying. Let's look at some other examples. So they ask us to look at these 3 tables, and you can see that table A is a linear pattern. It's increasing by 45 bacteria every day. And you can see that right here. But then if you look at table B and table C, they're increasing by more than 45 each time. Here's 45, but then we increase by 90, and then we increase by 180, and then by 360, and so it is doubling. So both B and C represent the same idea. And the general rule would be 45 is your initial, but then 2 is your multiplier. This next part asks us to figure out how much of the initial value has been multiplied after 4 days. Well, it's been multiplied 4 days. The days is your X value. And then how about after 9 days? Well, after 9 days, it would look like 9 days of multiplying by 2, and it would be about 23,040. Here's another example. Without performing any multiplication, what does it look like to simplify this multiplication? And if you look at the number of 2's, there's 7 of them. So that means there's 2 to the 7th power. And we started with 45 initially. Then, what is the value of each of the following numerical expressions? Well, 2 to the 2nd is 4. What's 4 times 45? 180. What's 2 to the 1st? 2. 2 times 45, 90. What's 2 to the 0 power? We know that is 1. Think way back to the start of the year. 2 to the 0 power is 1. Times 45 is 45. So the exponent tells us the number of days, and these represent the number of days of bacteria. Then we get into some more progress. So this first one, which of the following expressions are equivalent to 60 times 3 to the 5th power? Well, we could calculate it, and that's 14,580. Or if we expand it, here is expanded. We see that there's 3 raised to the 5th power. So there's 5 3's being multiplied. Then over here, it asks you to fill in what are these missing pieces. So the initial value is 60, and each day the number of bacteria is multiplied by 3. And remember, the exponent is your time, so that 5 right there is the number of days. This next one was an interactive, but it didn't work so well for me. Maybe you'll have better luck. I was able to put in all of the missing information except for the linear equation. So I typed it in. And then the account will have $200 after 1 year. Well, they'll both have $200 after 1 year, because one grows by $100, but the other one doubles every year. So if we thought about these patterns, the first one would be 100, and this is account A, by the way, 100, and then grows the second day, the second year would be 200, and then add another 100, and then another 100, and so on. Then if you look at account B, you start with 100, but then it doubles. Well, what's 100 times 2? Well, that's 200. So the first 2 years, they look the same, but here's where exponential growth starts growing. Here we go. What's 200 times 2? 400. So where's 400 times 2? 800. So notice that by the 4th year, you have twice the amount of investment as you did if you started with option A. It just took 4 years to double what that value was. Okay, here's some other work it out questions, just filling in some details. Feel free to read that on your own. The next work it out example is just wanting you to sort which ones are linear, which ones are exponential, and which ones are neither. In I and J, there's definitely some growth or things going on, but there aren't details about how much growth is happening or the pattern or the rates of that growth. So we can't determine if it's linear or exponential. And then D and G are quadratic. Anything that requires that gravity, the dropping from a cliff, that is going to be quadratic. And then D, a rocket, that is a quadratic. If you think about the motion of the rocket, it's going to go up and then it's going to come down. And then this one, I tried. There's a glitch here. After clicking next, all the other examples go away. So I'm not sure what happened. But the first one, it says, select all the characteristics that apply to exponential functions. Well, we know the graph is curved, and we know it'll never cross the x-axis. Okay, when you plug in 0 for x, b to the 0 is what? 1. And when what's 1 times a? That's just a. So when there's no way that it's going to cross the x-axis. And if you're curious about what we call it when it never crosses the x-axis, it's called an asymptote. Feel free to look at the other lesson that highlights that as well. Okay, here is an example 2.1, and it says, make a table and a graph of the exponential function y equals to the x. And so here is the table showing the progression of that multiplication. Excuse me. Here is the graph. And then what happens to the slopes? Well, the slopes double each time. So this slope is a slope of 1, but then here's a slope of 2. 4 minus 2 over 2 minus 1. It's a slope of 2. Here's a slope of 4. 8 minus 4 is 4, and 3 minus 2 is 1. And then here is a slope of 8. 16 minus 8, 4 minus 3, so that's 8 over 1. And then this last one is 16. I'm sure you can predict the next one that would be way up here. Think about it. What's double 16? 32. So that next big slope would be 32. This last part is a couple progress questions. In which of the following cases is the function not exponential? And so when you're looking at this, you have to understand that if a was 0, then it would be a horizontal line. If b was 0, then you wouldn't have a multiplier. It would just be a constant function. And if b was equal to 1, then you would just have a linear function. And then lastly, if b was negative, the graph would switch between positive and negative values. Kind of hard to see. I'm going to highlight it. But one would go up and another part of it would go down. So it would definitely not be an exponential function. Have a great day.